Similar to the Sn2 mechanism, we have what's known as the Sn1 mechanism, which the one being unimolecular. Unimolecular because in the rate determining step there is only a single molecule involved. Right? So I'm going to use a similar 2-methyl propane type molecule as I did in the Sn2 example. But in this case, the bromine will be found on carbon 2, so it'll be 2-bromo-2-methylpropane, and that carbon is now a tertiary carbon. Tertiary is important because the tertiary carbon favors the Sn1 mechanism as opposed to the Sn2 mechanism. Right? This has to do with what you can see right here on the screen. All right, in the first step of this mechanism, this is a 2-step process. The bromine bond is broken when the electron pair from the carbon-bromine bond is donated to the bromine atom. Okay, this creates what is known as a carbocation intermediate. So that's you'll see there the 3-coordinate carbon with the positive charge. All right, so this is a formally positively charged carbon atom that only has 3 covalent bonds to those 3 carbons. This is inductively stabilized, all right, or this is stabilized, if you will, by inductive donation from the CH3s, which basically means those CH3s are able to push a little bit of electron density down towards that carbon atom to help stabilize the positive charge. This process works best in a polar protic solvent, okay, because the protic solvent will be more highly polarized, right, and will allow that carbocation to be more stabilized in solution. Right, so the first step there, that is an equilibrium step, and it's a slow process. All right, the carbon-bromine bond is a strong enough covalent bond, all right, and won't just break rapidly. Okay, so once you have a reactive carbocation intermediate, as soon as let's say a stronger nucleophile, such as hydroxide, is introduced, the reaction is very fast and immediately produces, in this case, the corresponding alcohol. Okay, again, acceptable type nucleophiles will be water, ammonia, cyanide, right? But the most common example, again, that we will see is the hydroxide ion to form some type of alcohol. This alcohol will be 2-methylpropan-2-ol as a product. Okay, we can see here the potential energy diagram, also known as an enthalpy level diagram. Right, we would represent the 2 steps of this process. Here we would have to show 2 separate humps and a little well in the middle. That little well actually corresponds to the carbocation intermediate. So I'll put a little star there. Okay, this species is actually what is formed at the little star there on my potential energy diagram. This means it could be isolated and characterized, all right, but it's that little well, again, know the term carbocation. All right, the first step you would want to make sure you draw with a much higher activation energy, because again, this is the rate determining step. So you'll want to make sure the peak of that first hump on your potential energy diagram is higher than the peak on the second one. Right, and if you were to write a rate law for this, it would be rate is equal to the rate constant simply times the concentration of the alkyl halide that we started with. Okay, so some overall takeaways. Sn1 is faster than an Sn2 mechanism. Okay, and a secondary carbon, all right, as I've not covered it, can proceed by both the Sn1 or Sn2 mechanisms. Right, we would find evidence that both will have occurred.